So why do we use springs? Their application is good for what? You've all used springs, right? Where? Why? Does your car have one? It has more than one, I think. I hope. Otherwise, you'd be in trouble. So in that case, it's essentially to take a little bit of the energy if you hit a bump or something like that, and then release it slowly through your shocks. In general, however, and in most cases, we use springs in order to produce large elastic deformations. Remember that every elastic member, such as an axially loaded member or a beam which is loaded either by a torque or by a moment or by a force, can all assume to be springs. You can assume every one of them to be a spring, but in most cases, they don't give you very large elastic deformations. They give you elastic deformations a little bit, but not very much. If you want large elastic deformations, they will yield. Springs, on the other hand, compression springs, such as you see on the screen, are used to produce large elastic deformations through to do the manipulation of the geometry of the part. In other words, rather than the deflection or the deformation coming through an actual extension of a member, it comes from closing and opening a coil. So in that manner, it is much easier to produce these large axial, in this case axial, deformations. There are different types of springs. What you're looking at on the board is called a compression spring. The forces that we put on it, essentially compressive forces. There is a tension spring, which is similar to this, except that coils are wound shut like that. And then, of course, you're going to have some sort of a hook or something here so that you can apply a load. We'll take a look at some pictures of those probably next week. So that's called a tension spring. And it's wound shut with a preload so that initially when you apply a very small amount of load, you basically get no deflection until you overcome that preload. But again, we'll take a look at that in detail a little bit later. You can also have springs which produce deflection by bending. Such as a car leaf spring. They don't use them that often anymore, but if you look at old cars or trucks, they do use leaf springs. These give you deflections through bending. We can have flat springs. We can have constant force springs. Constant stress springs, so that the spring looks like a cantilever, essentially. If you look at it from the side, it looks like this. And generally, If you have a cross-sectional area here that looks like that, well, then your stresses are maximum over here. But if you look at the spring from the top and you see something like this, in other words, the surface on top is a triangle. So this is your fixed end. And the force is applied like that. So you can design that spring so that the stress will be constant due to the applied load all over the spring. No maximum stress, minimum stress, same stress all over. The springs could also be non-linear. Not all springs are linear. There's a good section in the book regarding different types of springs, and you should read that and be familiar with those springs. Something very similar to leaf springs are springs that are used as washers like this. Called spring washers. Here, when you apply load over here to a bolt, and there's usually a bolt sitting over here, like that. When you tighten the bolt, that spring deforms and essentially provides your preload. That's what it is. You can have coil springs. And coil springs are very, very old, actually. How old exactly, I don't know, but as old as clocks are. The spring that is used in old clocks and even watches up to about 60, 70 years ago, I suppose, were or had a spring that looked like this. Looks like that. So when you wind the spring, you wind this and you sort of make it shut like that. And of course, it needs to open up. As it opens up, it moves the dials. And of course, there are some design-related requirements here. You can also have this, of course, is this spring relates an applied moment to a produced change of angle or rotation. The same thing can be done in torsional springs, which look very similar to tension springs, except that you put torques on them. If you get a chance next time you're in Home Depot, take a look at mouse traps. They lose that kind of spring. So that also relates torque to an angular deflection. They can be made out of round or square wire. Most of what we use are made out of round wire, but you can have square wire. And there are some specialty springs specifically designed for a particular purpose, and you can design the body of the spring to do what you like. For our purposes, however, we will take a look at the compression spring first, and then we'll also take a look at tension and torsion springs. So there's the spring here made of these coils. The way they make these springs is that they take the wire and they wound it around the mandrel. And sometimes they use high-strength wire, sometimes low-strength wire, hardcore, cold work, all sorts of these. And once you do that and you secure the spring, in other words, plastically deform it around the mandrel, then it takes this shape and it more or less keeps that shape until you, such time that you may apply a very large compressive strength to yield it. Although if designed well, compression springs should not yield even if you take them to solid height. In other words, even if you take this spring even if you apply a force and this spring looks like this, still should not yield if designed properly. But if you put tension on it, of course it will. And if you insist on yielding it, it will yield. What we would like to do is come up with a scheme in order to calculate the stresses that are induced in the spring when a load is applied to it. And we're just going to do that right now. To do that, we need a few definitions that will be used in the equations that calculate stress and whatnot. So let's give you those definitions. D, whoops. Yeah, I guess mean, I was going to say average, mean coil diameter, as you see on the screen. Mean coil diameter from the center of one wire to essentially across the spring to the center of another coil. D, wire diameter. And we also define a constant, C, which is the ratio of D over D. This tells you how narrow or wide a spring is. It's called spring index. This is not the spring constant. This is not the ratio of the force to deflection. This is the spring index. It only defines the geometry of the spring. It has nothing to do with the applied load. Well, it comes into the equation for the stresses and all, but it doesn't give you anything else except the ratio of these two diameters. So when the spring is loaded, and now take a look at the free body diagram on the right-hand side on the spring. The spring is loaded, as you see on the left-hand side. And I cut a section here, right there, just like you would in any other free body diagram. Remember when you did beams? This is what you did. Simply supported beam, a load over here. You want to find what the load is here. You make a cut. And you say that in order for this right-hand part to be in equilibrium, the only way that is possible is that there must be a force there like that equal to it. There is no other place for that force to exist. And of course, then these two create a counterclockwise couple. So you say, well, it's got to be a clockwise couple in here as well. And that will give you equilibrium. Exactly the same thing is done there. So when we make the cut, the only location where a force can exist to counteract that applied force is right here on that surface. And those two forces must be equal. Well, those two forces create a couple. And therefore, the only place, again, that couple can be resisted is right where you cut. And therefore, the couple must be here. T, whose magnitude is equal to one of these forces multiplied by the moment arm of the couple, which is half the mean coil diameter. So if we look at that cut section, it's under a torque, T, and a shear force, F. So shear stresses are found. One, due to the direct shear force, the other due to the applied torque. So we say tau is equal to Tc over J plus F over A. Tau max, the maximum stress in the coil or wire diameter. So take a look at that. T equals Fd over 2. C equals D over 2. J equals pi times D to the 4th over 32. Or if you want to put it in terms of radius, D over 2, that's fine too. And A equals pi D squared over 4. So two shear stresses are produced, one due to the direct shear load, the other one due to the applied torque. The sum of those two, there are locations on the wire where these two add, and there are locations where they subtract. Because remember that the direction of this is constant. Shear stress is always like that. But this produces shear stresses on that side going downward and on that side going upward. Is everybody okay with that, or would you like me to draw a diagram of the stresses? Which one? You okay? Everybody okay? All right. So, if we substitute these into this equation, this is what we get. We get tau equals 4F divided by pi d squared plus 8FD divided by pi d cubed. If we now make use of the spring index and substitute in here in terms of the spring index, this is what we get. Let's say with C equals D over D, get tau equals Ks times 8FD divided by pi d cubed, where Ks called shear stress correction factor is equal to C plus 1 divided by 2C. Now, the term correction factor I personally do not like because there's no error to correct. It's just a way to write this equation in a simpler fashion. Notice that as soon as you have a spring, you have that. If you have a spring, you know what its mean coil diameter is. By the way, mean coil diameter can also be written like this. The outer diameter of the spring minus a wire diameter. A radius taken off from each side. So that's the only reason why we do this. Otherwise, there's no correction here. The value of C for regular springs should be somewhere between 4 and 12. If it is any more than 12, it's just too big insofar as the relationship between the coil diameter and wire diameter is concerned. If it's very small, then it's very narrow. So good meaningful values of C should be taken somewhere between those two values. So when we do spring design, we have to make an assumption. We don't know what C is going to come up to be. We make an assumption here, usually on the value of C. The best thing is to take a middle value, like a 7 or an 8, something like that. 9 maybe at most, depend if you have experience and you know what you're looking for. But the middle value would be fine, and then you can take your design from there. We will take a look at a design problem in one of the example problems that I will do. While we are on this KS business called correction factors, which actually is no correction, we also have to take note of the fact that there is a curvature here. And similar to all curvatures that we have seen so far, these curvatures produce larger stresses where the radius of curvature is small inside of this. And we've used stress concentration factors to represent this. Remember the fatigue problem with the leaf spring and bending? We said curvature. We use a stress concentration factor of 1.5 or something like that. This is the same. It increases the stress on the inside of the wire and decreases the stress on the outside of the wire. But the amount of increase on the inside of the wire is much larger than the decrease on the outside of the wire. So the inside of the wire becomes the more critical point to take a look at. To take account of that curvature and use it like a stress concentration factor, we use these factors. Kw equals 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C. This is called Wahl's factor. Or Kb equals 4C plus 2 divided by 4C minus 3. This is called Bergstrasser factor. These two factors, both of them, take into consideration the curvature, an increase of the stress due to that curvature on the inside of the wire. And they also include Ks. So when we use either of these two, we take care of that, and we take care of the stress concentration factor as well. So once we have that, we just simply multiply Kb rather than Ks by that. We will have taken care of both the shear stress correction factor and the stress concentration factor. Before we take a break, let me just say a couple of words about this gentleman. The other guy, I don't know this guy. He was one of the, both of these, of course, are found experimentally. There's nothing you can prove. This guy had done a lot of very good work a long time ago on springs. So if you ever have to design a spring or you know about the design of springs, he has a very good book called Spring Design under his name. And I believe we have a copy in the library. It's an old book, but it's a very good book. You may even nowadays find it on the web as well. But these are the factors that we're going to be using. My suggestion to you is to use this factor because it's easier, that's all. Other than that, you're free to use either Kw or Kb, whichever you like, makes no difference. Any questions? Okay, let's take a break. If you have any questions about your test, please see me. helical spring, compression springs. Because the aim is, remember, that we want to make large elastic deformations or deflections. To do that, we use Castigliano's equation. The spring is under two loads, the spring wire, that is, under two loads, a torque and a direct shear force. Therefore, the strain energy that is stored in it comes from those two sources. Under an applied force F, both of those are constant. They don't change unless you change the force F. But if the force F doesn't change, neither of those two will change. So the strain energy for a constant torque, if you recall from Castigliano's equation at the beginning of the quarter, T squared L over 2 GJ, and that from a direct shear force, F squared L over 2 AG. That's the total strain energy in the wire. Before we go any further, let's see what each of these mean. What is L? I'm sorry, come again, please? The length of the spring. Do you mean this length, the length shown on that screen? Yeah. Not quite. Remember what we did when we were doing Castigliano's? Whether we were doing something in bending, let's say like that, or something in torsion like that. These were our L's, correct? The actual length of the member that is carrying stress. So as we look at this, the length of the member that is carrying these stresses, both the direct shear and the torque, is what length? Compressed length? No. What part of this spring, the coils, what part of the coils are under these loads? Clearly, where I've taken this cut, that's under these loads, right? What about any other cut, any other place in the spring? Will it also be under those loads? Sure. And how does that length go? Spiral, correct? In other words, think of it this way. It's just like this, except if you open it up. Open up the coils. Get a big, long member, which is under torsion and under direct shear. So the length is pi times d times n. Now, sometimes n is the number of coils. Sometimes we specify that as n sub a. I'm going to take a look at your book, see if they do say n sub a or not. I'll define what n sub a means in just a minute. Yeah, they do use n sub a, but let's see if they also use it in these equations. No, they don't use it in the equations. Okay. Where n, which is the same as n sub a, is the number of active coils. We'll define in just a little bit what that means. As you will see, not all coils in the spring are active. Not all of them carry these loads. So that's L. G, modulus of rigidity of the spring material of the wire. J, pi d to the fourth over 32. Remember, d is the wire diameter. A, pi d squared over 4. And if we substitute all of these into this equation, this is what we find. U equals 4f squared d cubed n divided by d to the fourth g plus 2f squared d n divided by d squared g. The first part of this energy term is related to the torque. The second part is related to the direct shear. And we know that the deflection at any point of a loaded structure, and that's what that is equal to partial of u with respect to a point force applied to the member. And that'll give you the deflection at the point of application of the force. So we take the derivative of this. We get 8f d cubed n divided by d to the fourth g plus 4f dn divided by d squared g. And if we now substitute for d over d, the value of the spring index, which we have defined, C equals d over d. Notice we have a d cubed over d cubed here. We have a d over d here. If we substitute that and rewrite this equation, this is what it will look like. Y equals 8f d cubed n. And remember, n is the number of active coils, not the total number of coils. They may be different. They don't have to be different, but they may be different. Times 1 plus 1 over 2 c squared. The first part of this term, that is 1 multiplied by that, is the first part of that. And the second part, 1 over 2 squared multiplied by that gives you this, the second part. Oh, sorry. Shouldn't have pointed at the energy. First part is this, second part is that. The deflection, not the energy. That's the deflection. What's the maximum value of this? 1 over 2 c squared. Maximum practical value. What about the value of C? Between 12 and 4, right? So this will be maximum when C is equal to 4. Agreed? That's 1 over 32. A little better than 3%. Right? So that's about 0.03. And that's 1. 3% or 0.03 is negligible with respect to 1. So as an approximation, say y is approximately equal to 8f d cubed n divided by d to the fourth g And as you know, we define spring constant K is equal to F divided by Y, load divided by deflection. And if you take a look here, F divided by Y is equal to d to the fourth d divided by 8d cubed n. So that comes out to be equal to d to the fourth g, approximately, d to the fourth g divided by 8 d cubed n. So knowing the geometry of the spring, capital D and lowercase d, and also the number of coils, of course, and the properties of the spring material, we can calculate the spring constant. And that is a very good equation for calculating spring constant. It is slightly approximate, but the approximation is not that much. And it deals with the, or agrees with the experimental results. Any questions? Okay. Now, remember I was just talking about N, calling it Na, number of active coils and all of that. I'll bring you some spring samples next time to take a look at. But springs can be cut, after they're wound, can be cut and treated in different ways. One way is once you wind the spring around the mantle, just cut it like that. Nothing else. Simple cut. If this is the case, if this spring sits against a flat plate, I'm exaggerating. Let's say 2 flat plates. Only one point of the spring will be in contact with that flat plate, theoretically. In other words, all parts of the spring will carry those loads. However, you can do this. You can square the ends like that and grind them. That crosshatch means it's ground. Or you can square them and not grind them, such as that. Or, rather than just cutting them, which is called plain end, you can grind it a little bit and flatten it out. The result of all of these is that a part or all of one of the end coils, or both end coils, sits flat against this plate. So if I have a squared or a squared and ground spring, it will look like this. So I may have a whole coil, in fact, in this case I will, may have a whole coil flat against that flat plate. The part that sits against these flat plates carries no torque and no shear load. Therefore, no strain energy is there. It stores no strain energy, therefore it can't be a part of this equation. So that's what we mean by active coils. Active coils are those coils that actually carry the torque and the direct shear force and store energy. And if we have cases like this, you simply count the number of coils if nothing else is available. And in this case, call it N equals the number of active coils. Nothing else needed. In that case, you approximately have to take out, if it's at both ends, you approximately have to take out one coil at one end and one coil at the other end. Same thing over here. And if it's ground, it's about half a coil at each end. So that the number of active coils would now be different from the total number of coils. This table in your book shows you the end coils. NE means end coils. In plane, you have none. In plane and ground, you have one. If it's plane, just grind it. Square and closed, or square and closed and ground. And you do see a little bit of difference in the free length here and the solid length. And let me define that too in just a minute. You'll see a little bit of difference insofar as these lengths are concerned. Those differences are really very, very minor. For example, take a look here. This is the free length P. P is the pitch. I'll define it in just a second. Times number of active coils plus 3 times the wire diameter. Here, same thing, 2 times the wire diameter. Remember, wire diameter is very small with respect to coil diameter in general. And so there really isn't that much difference. I would just simply take off 2 coils if you're here or here, 1 if you're here, and none if you're there, and not worry about these equations to try to apply them exactly the way they are. The free length of the spring, as the name implies, is the length of the spring with no load on it. Free length. The solid length is that. You push the spring to solid height. You do not want to reach this situation at all during operation, because the spring is no longer a spring if you do that. Therefore, we have factors similar to the factors of safety, which guard against reaching the solid height. However, should you reach that solid height by mistake or by somebody overloading the spring inadvertently, you don't want the spring to yield. So even when compressed to its solid height, it should not yield. So that when you take the load off, you're still capable of using the same spring. But you shouldn't reach the solid height at all. Free length, solid length, pitch, as you would expect. The distance between a point or similar points on adjacent coils. It's called the pitch. Very similar to the pitch in threads, in bolts. Any questions? Now, let me just take a quick look at your book, Deflection. Okay. Very similar to columns, springs may also buckle. If you have a very long spring and you try to deflect it too much, long and narrow like that. If you try to deflect that too much, there's this possibility of buckling. Just like regular buckling that you studied in strength of materials. Whether or not a spring buckles depends on, similar to what you had in columns, a ratio called the cylinderness ratio. But its deflection calculations are much more complicated than that of columns. So let's give you the equation for what we call the critical deflection. How much can you deflect this spring before it buckles? That equation, found from considerations of theory of elasticity, looks like this. LO C1 1 minus C2 divided by lambda effective squared to the 1/2. In this equation, C1 and C2 are elastic constants defined in this manner. E divided by 2 times E minus G. C2 is equal to 2 pi squared times E minus G divided by 2G plus E. And lambda effective is called effective cylinderness ratio. And it's given by alpha LO over D. Free length divided by the diameter. In the equation for lambda effective, in the C1 and C2 equations, the nomenclature is self-explanatory. Modulus of elasticity, modulus of rigidity, or modulus of elasticity in shear. There, LO, the free length, D, mean coil diameter, alpha is called end condition coefficient. And it is very, very similar to that of columns in that if you have a spring whose ends are plane, like this, just always assume them between flat parallel plates. See how much they're in contact with those flat parallel plates, and you will know the end condition. This is similar to the pin-pin condition in a column. So when this thing buckles, it just buckles like that. So I'll actually give you the equivalent of columns. Draw it larger. The equivalent of this is a pin-pin column, and it buckles like that. And for this, as you can see from here, both ends pivoted, the constant alpha is 1. In other words, it's L over D, just like you had it in columns. For any other type of condition, you have to find an effective length to calculate lambda effective. So these are your other possibilities. Pin fixed, just like the column. In columns you had, this is, for columns is 0.7, for this is 0.707. And you get this when you have one end plane, the other one ground, and squared against a flat plate. So this becomes your fixed end, that's your pin end. For this, it's 0.707. For fixed, column would look like this. The buckled shape of the column will look like this. That's the effective length, L over 2. So this is alpha equal to 0.5. The effective length is half of the total length. And there's one, both in columns and springs. You can have one end fixed, the other one free. There's the applied load, and that's the deflected shape. And this length when finished to mimic a pin-pinned column, it's 2L. So for this case, this is this case, fixed here, free there. The coefficient alpha is 2. You always try to find a situation where you can fit a pin column. So that's how they buckle, and those are the effective lengths. Now, in order to design a spring, we want to make sure that buckling doesn't occur, meaning that there is no deflection. Why critical? There's no real value of this deflection. Why critical? That will make the spring buckle, meaning that you can compress the spring to its solid height and it will not buckle. We would like to design springs that do that instead of buckling. Therefore, we must make sure that such deflection does not exist, that there is no way we can put that deflection on the member. So take a look at this. How can we have Y critical be non-existent? How can we not find any real value for Y critical? What if this is negative? Then it will have no real value, will it? You're taking the square root of a negative number, it will have an imaginary square root, but no real one. Therefore, we must make sure that this is never positive. Meaning that you must make sure for stability Y critical must not have a real value, or C2 over lambda effective squared must be greater than 1. If we now substitute for lambda effective from this equation, you will find a relationship between the free length and the mean coil diameter. That relationship looks like this. LO must be less than, or, well, I'll just forego the, I suppose you could put the equal sign, it's okay. Pi d over alpha times 2 times E minus G divided by 2G plus E. To the 1/2. So once you find once you know what your material is, what the mean coil diameter of the spring is, how it is being supported, you can calculate the maximum value of the free length. Because the larger the free length, the easier the buckling. For steels, in other words, if we substitute steel properties here, LO must be less than 2.63 D over alpha. If that's the case, then there will be no buckling for steels. For other materials, you put in the E and G and you come up with your own equation. Any questions? There is one section in your book where they talk about presetting or set removal. Let me write that and then I'll explain what that is. Now, on the face of it, those two appear to be contradictory. Presetting sounds like something we're doing to the spring. Set removal sounds like something we're taking away from the spring. But they both mean the same thing. And what this means is that if you want a spring, let's say that height, you design the spring, and of course you have to make calculations and see what the design length should be. You design the spring somewhat larger than that. And then you put a force on the spring, you bring it to solid height. In which process the spring must yield. In other words, your calculations must be such that if you deflect the spring to its solid height, the spring material will yield. And we have the equations for tau, and you know the yield shear stress for the material. You make sure that tau goes beyond the mean shear stress. How much beyond it depends on the difference between these two. You make sure that this yields, but after you take the load off, so you bring this to this shape, in which process this is the solid height. That's the free length, and that's somewhat larger than the free length. We bring it to solid height. Then we'll take the load off. Guess I better put a load here. And once we take the load off, if we have done everything correctly, the spring will have the desired length. Now, the reason why we do this is that anytime you deform a material plastically, and remember this has to yield, so that's plastic deformation. Anytime you deform a material plastically and then unload it, stresses will remain in the material called residual stresses. So this part contains residual stresses. And these residual stresses will be in the opposite direction of the stresses that will be induced in the part, in this case the spring, due to an applied load. So, let me go over that one more time. If you load the material beyond its elastic limit so that there will be plastic deformation in it, and then allow it, and then unload it, the stresses that are set up in this are in the opposite direction of the stresses that would be produced by the loading. What that means is you can apply a higher load to the material and still keep the stresses reasonably below the yield strength of the material. That's called presetting or set removal. Let me give you, I think I have enough time. Do you have any questions on this? We do that essentially to strengthen the steel. Let me show you this table before I do that. Take a look at this, not that one. How about that one? No. Let me... Ah, there we go. Take a look at this table. There's the material. Music wire is one of the main materials that we use for spring. Then most materials for spring are very high strength. Maximum % of tensile strength, that's your maximum allowable torsional stress. Before set removal, in other words, before you go through that operation, this maximum is only 45%. The allowable is 45% of the tensile strength. After you do that, 60 to 70%. So you can apply a higher load to it if you have a presetting. The reason why these stresses are set up in the material in the opposite direction is that anytime you deform a material beyond the elastic limit and it yields, let's just talk about torsion right now. Let's say you have that, because that's basically what this is. And let's say our shear stress strain diagram looks like this. That's very idealized. It's usually like that. And we can do either one, doesn't matter. We load beyond the elastic limit. That means, this is tau and gamma, by the way. This is shear strain, not normal. Let's say we go up to this strain. If I draw a shear stress diagram for this, here's your cross section. At this point, which is the outer point of the shaft here, I have this strain. Point next to it, and that gives me that stress. This is SSY, by the way, yield shear stress, SSY. And next point next to it, same stress. Next, well, actually I should come down this way. Next stress, and I'm getting closer and closer to the center now. And the strains are decreasing. Tau gamma. This is gamma max. And finally, I get to this point. Let's say it's over here. And then eventually, it comes down to 0. So this is my shear stress diagram. You drew these diagrams in strength, right? Except that you didn't go into the nonlinear part. You can. When we unload, however, the unloading doesn't come back like this. It goes down like that. So that's the loading. That's the unloading. And by unloading, I mean whatever torque I have here, I come around and put another torque on top of that of equal magnitude, but in opposite direction. That's the meaning of unloading. Stresses due to this torque will now look like this. Linear. The difference between, this is not related to the subject in this course, but it's good, it's something good for you to know, just in case you come across it. So somebody asks, what are residual stresses? You can say you know something about them. So the difference between these two stresses, and this red stress is in the other direction, by the way. It's in this direction. I don't want to draw the rest of it. The difference between the two is this. And notice that the red stress is larger than the black stress. So the net residual stress, this is the net residual stress here, is in this direction, which is in the opposite direction of the originally applied load. Therefore, now when you apply that load, first you have to overcome that. And then you load the material. And that's why the material becomes stronger. So that's the reason why we do set removal or presetting. Any questions? Okay, let me take a look and make sure that I have not forgotten anything. No, that's it. Next week is the 10th week, and I usually don't give a quiz on the 10th week. However, if some of you think that by taking another quiz you can improve your grades, I'm willing to make a quiz and give it to both sections during the university hour, either on Tuesday or Thursday. It really doesn't matter, whichever. So if you think you would like to do that, email me. And then if there's at least a few people who email, then I can give you another quiz. But it will be optional. In other words, you don't need to take it. You don't have to take it. If you like the average that you have so far, just leave it like that. And if you won't take it, then you take it. But if you do take it, it will count. It is not dropping the lowest grade. So I want to make that very clear. But still, if you want to do that, you are welcome to email me, and maybe I'll just make it on Thursday so I can tell you on Tuesday whether there will be a quiz or not. And it will be on the material essentially covered in the last midterm. It won't be on springs, although we could do it on springs if it's on Thursday, because I'll be finished with springs by then.